Alright, this is the beginning of AP review videos. So I'm going to make a review video about each unit, and hopefully that'll be helpful for preparing for the AP test and just filling in gaps of your knowledge. I'll leave, this will probably be a really long video, I don't know how long, but I'll leave like little things in the description so you can like jump to, and yeah, just like, you know, if you want to review like asymmetric launches, you just go there. This video is all about kinematics, so I'm going to kind of review some of the key things of kinematics. I'm going to start like sort of the conceptual background with kinematics and like sort of just wrapping your head around it. And then I'll just kind of talk about some like things to know, like just some things, some skills that they'll definitely ask, and stuff like that. So let's just start with sort of the conceptual background here. Kinematics, like what is kinematics? If someone had to ask you like what is kinematics, what I would say is kinematics is really the study of just predicting motion, right? Kinematics is not concerned with like how does motion work, right? We can explain motion with forces, with, you know, energy, with momentum, with rotation, right? We can explain why things move the way they move, but kinematics is really just about predicting that. And that's why it's really math heavy. That's why our first test didn't have SCP-6, because it's not really explaining motion. There's not much to really explain. It's just how motion moves. We can model it graphically and mathematically. So let's just get started with our first study of motion, the Speedy lab. We did the Speedy lab at the very first day of Physics 1. And we had the little car, right? It was, you know, it was a cool, I forgot, it was like probably a dune buggy or something. And it was moving a velocity, and we had to measure like the position at certain time intervals. And by doing that, I'm going to use a bit of a darker marker here, but by our graph and pivot or whatever you used, you should have gotten like a position versus time graph like so. Alright, so we got a straight linear line. So what does this mean, right? Well, what is this telling us? Well, at one time interval, it moved like this much. And then on a second time interval, like the same amount, it moved the same amount. And then for the third time interval, it moved the same amount. Like if you know, imagine it going through each time interval, like it was going the same amount each time. So this slope, right, the slope is our change in y-axis over the change in x-axis, or in other words, change in x over change in t. That was constant. For every time interval, it was going the same change in x, like it was going the same amount. So it's just some vocabulary to remember. This is displacement, right? Your change in position is displacement, and this right here is velocity. So velocity is the first, I guess, key term where it's speed with direction, right? It's your change in position over a change in time. So if you're moving in a straight line, you have a constant velocity. That's really just what velocity is, how much are you displacing. So if you have a straight line, straight constant velocity, that means your speed is constant and your direction is constant. I think. I don't know what scenario where your velocity is the same but your speed is changing. I don't think that exists, but I could be wrong. Velocity times time, constant velocity, right? Every time interval you have the same velocity. So, key things, just some conceptual things to understand is that the slope is the velocity, right? The change in x over change in time is just the velocity. So you have a constant slope, you have a constant velocity graph. The area under the curve is the position. So, to my friends in calculus, you know, you can think of this as integrals are antiderivatives. So if the integral of this velocity versus time graph, it's like, you know, I actually haven't taken calculus, so my terminology might be wrong, but you know, it's an antiderivative, right? Like the antiderivative of velocity is position versus time, the anti-slope or whatever. So that's one way to think about it. For my non-calculus friends, like me, the way I think about it is that, well, this forms a rectangle. The t is the base, and then the height is velocity. Base times height, velocity times time is equal to change in x. This is one of the first equations we learned. pretty simple equation. Hopefully it makes conceptual sense. Like if I'm going at 3 meters per second, then every second I'm displacing 3 meters, right? 3 meters per second. That's so in like 3 seconds I'll have displaced 9 meters. This is just what the equation is saying for constant velocity. So I don't know if you remember this day. I remember it pretty clearly. We went inside the classroom. We had to take we had to take like a ball, and we had to like predict how far, like how much time it was gonna take to displace this. Like displace that amount. We predicted a time, and I think what was it? We got like it was like maybe I don't know. I don't remember. We guessed a time by using this equation, right? We figured out the velocity. I'm sorry. That's what we're predicting. We had a photo gate, and we had to figure out like what was the velocity. So we had the time, we had the change in x. We just had to figure out what was, or we measured the time, we had the change in x, which would predict the velocity, and we were off. This was like half off. This wasn't like an experimental error. We were off. So what was different? Like we could use this to predict. Like the constant velocity. What was different here? Acceleration. That's the next big thing. Acceleration. So we did the Speedier lab. So let's kind of let's investigate acceleration a bit more. This is just conceptual stuff. So after this, I'm gonna actually get into the skills. But I think you might have skipped this if it was already getting boring. Okay. So when we did the same thing for the Speedier lab. We noted the displacement versus like several time intervals, and what we found is it actually makes, when you plot the points, it makes a quadratic relationship. So like the slope is constantly changing. So the slope initially is 0, and we get that from the tangent line. So the tangent line is like the sort of instantaneous slope. So if we think about each point here, the tangent line is getting steeper and steeper. And the way I like using the tangent line is just using the marker here, and just, you can see it's gradually getting bigger and bigger. The velocity is gradually increasing. So if we were to draw that in velocity versus time, we got something like this. And acceleration versus time, let's just talk about this graph real quick, right? It starts at 0 and then goes to its final speed, just like it starts at 0, goes to its final speed, and the slope is acceleration. So, because if you have change in v over change in t, that's how quickly your velocity is changing. We call this acceleration. So in other words, velocity final is going to equal velocity initial plus acceleration times time. Awesome. So some key things and I think now I'm going to start getting into some math stuff. So we have this equation. Okay, this is the v final equals v initial plus acceleration times time. Then we have the next equation, which I'm not going to get into like where this comes from, but I highly encourage thinking about like where does this come from. You can watch videos, but I just for the sake of time, change in x equals 1/2 acceleration times time squared plus v naught times time. So this is a second equation. We have v final squared equals v initial squared plus 2 times acceleration times change in x. And then finally, is there any more? These are the 3 I like the most. I'm trying to think, is there any more? I don't think there's any more. There are more, but I mean, like, these are the 3 I'd say must know for sure, because you can do basically any kinematics problem with just these. Yeah, so let's talk about how do we use these, like where would we find them? Well, we'll find them in all sorts of problems where like we have a car and we want to figure out like it starts at 0 and then it's it accelerates at 2 meters per second every second, 2 meters per second squared. Well, like how far will it end up in like 3 seconds, we use this equation. We no longer can use change in x equals velocity times time. This equation is like only works for constant velocity scenarios, and this is not constant velocity. It starts at 0 and then it's moving faster and faster. This is not constant velocity. One way I like to think about it is if we actually take this equation, the 1/2 at squared. One really neat thing is that for a constant velocity scenario, what is the acceleration? It's 0. So this whole thing becomes 0. You're left with change in x equals v naught times time, which is basically this equation, right? Because if you think about it, the initial velocity is constant throughout the entire thing. So just remembering those kind of problems, you'll get a bunch of problems where they'll give you some of the variables, and then you just have to figure out the third. So it's really a thing of like, okay, I need to figure out change in x. I'm given time. I'm given the acceleration, and I'm given the initial velocity of 0. What I'm not given is final velocity. So for sure, I'm not going to use this one because I don't know what final velocity is. So I would just use this one, right? So that's really the very basic problem you'll get. Some problems are a bit harder though. You'll get some kind of think of a problem on the spot. Just some problem that you can get. So maybe you'll have a ball rolling down a ramp. Okay, let's do this. It starts at rest, and you know the final velocity is 10 meters per second, and you have to figure out how long it. Oh, that's kind of. Oh yeah, let's do that. How long? Or no, can we do that? I'm trying to think of a two-step problem. You could have something like, okay, fine. Okay, fine. Maybe they'll give you time. So it takes 3 seconds to roll. What's the distance? So I'm trying to think. So now this is interesting because you have time, you have v initial, you have v final. So I'll say 0, 10, you have our change in x. We need to figure out what that is. Oh wait, no, we know time is 3 seconds. And then we don't have acceleration. And this is one of those things where you need to figure out what the acceleration is because the acceleration is in all of these equations. So if they don't give you the acceleration, you're going to have to, like first you might have to use these, so your t, v initial, v final for this equation to figure out what acceleration is. And then once you have acceleration, you would use maybe this and time and stuff, and then you can figure out how long the ramp is. And it's just stuff like that, two-step problems. So yeah, those are your kind of basic-ish kinematics problems. Just remembering how to do those. I'll tell you something, very rarely they'll ask you like do it with kinematics. Because they're multiple choice, like you can do it with energy, you could do it with momentum. And when we get to those topics, I'll kind of talk about how you can sort of replace them with kinematics. But still, knowing kinematics is very helpful. I'm gonna get into vertical stuff. So let me just see. Oh, one other thing I forgot to talk about. Another very important skill. If they give you a graph like this, you gotta figure out how do we draw the rest. And my best advice for graphs like these is just look at the slope. Initially, the slope is high, so it is a high velocity. And then we can see, and we'll assume it's like quadratic from this point. It's like a, what do you call it, concave up. You can see, okay, it's approaching 0. The slope approaches 0, so our v versus t must approach a t-axis. And then it starts going up. It's like starting to speed up, so we would draw it like that, right? And then you would draw your acceleration. It's just a slope, so we'd have negative stuff, positive stuff. I think we've done a lot of graphs like this. but hopefully just a good skill to have, just being able to piece over graphs together. So yeah, let's get on to Freefall and stuff. Just take some notes about that. Let me see how much time we're at, just so that I'm not, going too far. Okay, 15 minutes, not bad. So let's go into Freefall. Freefall. If you have an apple, or if you have a boulder, they're both going to accelerate with the same, same acceleration. I'm saying negative g. It can also be negative 9.8. G is like a positive number. I'll use actually negative 9.8. That'll make more sense. All objects on Earth will accelerate at negative 9.8, no matter their mass. Even a feather. Now, if you take a feather, over your one foot and then a hammer over another, you could tell me which foot you're gonna feel first. It's gonna be the hammer. You're gonna feel the hammer like instantly, and the feather is gonna take its time to drop. But that's because of air resistance, and I believe on the AP Physics test, all problems have air resistance neglected unless otherwise stated. So a feather will also, fall at the same rate. Now, remember, this is kinematics. We're not explaining motion, we're just predicting it. Forces explains why this is true, and I'll cover that in my forces thing. I'll tell you right now, F equals ma, mg is the F net, so F net is equal to ma. Atoms cancel out, mass doesn't matter, and then we'll explain that more in forces. But remember, they all accelerate at the same rate. So the thing about freefall is you can get problems like, okay, I launch it up, and it reaches a max height of 3 meters. You have to figure out the initial velocity, the final velocity, and everything else. And let's actually go through that. This is a cool practicing to do. You just know this ball is going to reach a max height of 3 meters. And you got to figure out, okay, what's the V initial? What's the V final? What's the acceleration? What's the time it's in the air? And you can figure that all out just by being given the change in Y is 3 meters. So, first of all, this is kind of a trick because we know the acceleration is going to be negative 9.8. And that's really how you can find everything else. Because then you would just do, okay, change in Y is going to equal 1/2 AT squared plus V naught times time. Shoot, I don't know what the initial velocity is. Oh, that's okay. What we can do is we can realize that, okay, it's actually going to take half the time to get up here. So it actually should be T over 2. It's going to take half the time to reach up, and it's going to take half the time to fall down. And when it's falling down, the initial velocity is 0. So what you can actually treat it like is, instead of it taking, we can really just say, okay, we'll just set the problem like here. Like we'll set the initial starting point here, and then half the time it's going to take to fall down. So everything will work out like that. And then you just put a negative here because it's initially 3 meters up and then it goes down, so it's like negative 3 meters falling. And then you can solve for time. 6 meters over negative 9.8. You're going to take the square root and then multiply by 2. And then that will give you the time. And then once you have the time, you can figure out the initial velocity thrown up. And you can figure out the final velocity. Hint, V final will equal negative V initial, right? Because they're both at the same height. So if you throw it up, whatever the initial velocity is, when it's fall down, it's going to have the same speed, just downward. So V initial equals negative V final. You can think of it like that. And the reason for that is because V final is going to equal acceleration times time. And then we'll like here, we'll do it like this. T1, so like, okay, how do I explain this? V final is just going to be from here all the way down, right? So it's going to build speed as it's falling down. So the initial velocity will be 0 up at the top, and then it's going to take a certain amount of time to accelerate to V final, right? Now, let's think about V initial. from here to the top, the final velocity is 0 meters per second, and then you're going to have acceleration times t2 plus v initial. So we get that v initial, negative v initial, is equal to acceleration times time 2. Here's the key. T1 and T2 are the same. Why are they the same? Because it takes the same time to go all the way to this height, and it takes the same time to fall all the way back down. So if this is equal to that, negative v initial is equal to v final. So that's just something I thought I'd bring up. It's a really important key. And remember, this only works for the same height. Like if it's like returning back to the same height, right? Because you can imagine if it's going up and then it falls even more, it's not going to have the same velocity or same speed, just in the negative direction. It's going to be moving faster. So just some things to keep in mind. And with that, I thought I'd just go to some projectile stuff real quick. We really have three kinds of projectile launches, and they each get, frustratingly more annoying. We have our horizontal launch. So if we have something like this, we have our symmetrical launch. So if you have like a soccer ball you kick up and reaches the same height. And then we have our asymmetrical launches. So it's not going to reach the same height. Instead, like maybe it's a basketball, right? And then it's going into the basket. So I'm going to talk about each of them. First of all, horizontal launch problems. Okay. I love to go out into the streets and ask people this. If you took a gun and a bullet, and if you dropped the bullet and shot the gun completely horizontally, just like this, which one is going to hit the ground first? I think we all want to say bullet, or the shotgun, right? Well, the bullet's gonna drop first, and then you have your shot bullet. But they both take the same time. And let's talk about this. So, a big part of these kind of projectile launches is that their x and y, like the x motion and the y motion, are simultaneous but independent. So what does that mean? What that means is your v, right? That's all going to be directed in the x direction. Okay, wait, how do I'm going to just make this larger to help myself explain. It's going to fall a certain height, so it's going to follow a certain x, it's going to travel in the x direction, and it's also going to travel in the y direction. They're independent of each other. They don't like correlate, or how do I say this? They don't like, how do I explain this? They don't, I guess, affect each other. That's why the bullet and the shotgun will both like hit the ground at the same time, because the x motion is completely different. The bullet is moving way faster, or way farther, but that x direction motion does not affect its y direction motion. So if we think about the x direction motion, the change in x, let's say this, change in x, your change in x equals vx times time. Notice how I'm using the constant velocity equation, right? It's the vx, the component of the velocity in the x direction, is constant, because there's no acceleration. There's nothing in the air that's accelerating. There's no forces that are causing horizontal, acceleration. So, change in x equals vx times time. And then for the y direction motion, we have the change in y equals 1/2. Now take a look right here. 1/2 acceleration in the y direction times t squared plus v naught y times time. So notice, for the y direction motion, it is completely independent of the x direction motion, right? The change in y depends on the vertical acceleration and the vertical initial velocity. That's why for the shotgun and bullet that are shot and dropped at the same height, they have no component of the velocity directed upwards. If you think about it, if I shot the gun up, then obviously things are going to be different. If I shot it horizontally, each of them don't have a v naught y, so, same height and same acceleration because it's g, it's like negative 9.8. They have the same ay, they have the same change in y, so they're gonna have the same time. The thing that bridges your change in y and your change in x is the time. This is the thing that bridges them, because it'll take the same time to travel the horizontal distance as it does to fall. Like, that's what like makes them simultaneous, right? Because it's impossible for, you know, it's impossible for the thing to keep moving this way when it's hit the ground. Like, they have the same exact time. So that's a very key idea, and I think it's going to be even more important in the symmetrical launches. So let's actually look at those really quickly as well. So for symmetrical launches, let's draw our little ground, and we have this ball, and then we're going to launch it upwards. So now, the initial in order to give the soccer ball this kind of path, we got to give it an upwards directed velocity. So there's going to be a certain angle with the ground, and that angle in the ground is going to cause, well, not cause, but there's going to be a Vx and a Vy. So this is a right triangle. We can actually split up the components into this sort of, you know, we can split them up like this. So if we remember, we've done this all year. Vy is going to be V sine theta, because it's the opposite of that triangle. Vx is going to be cosine, because it's the adjacent of that triangle. So using that same logic, we can figure out that the range, right, this is it's like how far it'll go. That range is going to equal V cosine theta times time, because this is the x component, which is constant times time. And with the same sort of thinking, this max height is going to equal, so the max height is going to equal 1/2 AYT squared plus V0 y times time. This is actually wrong. If you're talking about time as in the whole time of the year, remember it's going to be half the time, because it's going to take half the time to reach the very top. So, and then obviously that V0 y, I didn't write it here, but then you would substitute that in. So very sort of similar to horizontal, except you just got to factor in the Vy. It's not going to be 0. That's why, like, depending on the angle you launch it, it's going to have different time in the air, because now the time in the air depends on this. I forgot to mention that. The time in the air, like, it depends on, like, the y direction stuff. Like, it depends on, like, the y direction motion. I mean, that's why, like if you have the same, like, if you're shooting the bullet and dropping the bullet, like, they're gonna have the same time in the air because their y direction motion is the exact same. So, you know, that's really just the basis of projectiles. So I'm gonna end things off with some asymmetrical stuff, and I'll also touch on graphing for a little bit. So for asymmetric, so let's enhance, or I don't know, enlarge that drawing. So this has always been the trickiest for me. I remember, like, when I took my first test, this was the thing I was really stressed about. So there are a couple of things to keep in mind. The max height, we can call it, let's say h max, and then we'll call the height that it reaches h naught. So let's say they ask you, what is the time in the air for, what's the time in the air for this basketball, right? Given the velocity, and we'll give, like, I don't know, 10 meters per second with an angle 60 degrees, right? So what you could do is say that, okay, h naught, so the height that it's going to reach. So initially it starts at 0 height, and then it's going to be at h naught. So the change in height is just h naught. And that's going to equal 1/2 AY t squared plus V naught. It's going to equal V naught times time. v naught y times time. You could do this, so if you did this for the symmetrical version, what that would look like is, well, it starts at 0, and it ends at 0, so the change in y is 0, so you could do 1/2 ay t squared plus v naught y times time, and then you could just subtract like the v naught from both sides, and then you can divide out a t, right? Because there's two solutions. We can divide out the t. This t would just give us like the solution when t is equal to 0, and then which like that doesn't make sense, like because obviously t equals 0 is like, oh yeah, whatever. You cancel those out, you would be able to figure out the time. This you can't just divide out a t, like you don't have 0 on the other side. You would have to do the quadratic formula. You'd have to like subtract out h, and then you have to do, you know, t equals opposite, whatever. What I like to do is I instead like to think about, okay, what is the time it takes to reach h max? And I'll add in the sine theta just to remember that we're dealing with components. And then, what is the time to go from h naught, or to go from h max to h naught? So h naught minus h max equals the same sort of equation, 1/2 a t2 squared, which equals, and there's no like v naught y t, right? Because it's at here the vy is 0. So then, you know, you could do that t is equal to t1 plus t2. So that's one way you can approach these kinds of problems. You can also do the quadratic method way. And yeah, we can also talk about graphing really quickly. So if we're just doing some graphs with like, you know, if we're doing graphs with like, so if we have, let's say x versus time, first let's do a symmetrical launch. X versus time, Vx versus time, Ax versus time. Then we have y versus time. We have Vy versus time. And then we have Ay versus time. Our graphs, well, let's just think about it. For x versus time, it's like that, right? It's constantly going at the same Vx, so it's gonna like go through the same distance in a constant time, or a constant velocity. So constant velocity, and then acceleration y, you know, it's gonna be 0. I'll just pretend that's 0. For y versus time, it initially has some velocity upwards, right? And then it's gonna come to an apex, and then it's gonna go down, like it's gonna reach the floor. Now, hey, this kind of looks like the path it made, and if you're in pre-calc honors, you can probably use parametrics to, like, you know, figure that out. But yeah, that's how y versus time would look, right? It's reaching its max height and then it reaches down. So, Vy versus time, so initially the velocity is upwards, and then it's going to be negative, right? We see it going from positive, 0, negative, positive, 0, negative. My calc friends, you probably know this relationship right here. And then for acceleration in the, acceleration y, it's going to just be negative 9.8, right? So it's just, this is how graphs will sort of look like, I guess. Yeah, I know I didn't cover everything in this review thing because there's a lot to kinematics, but hopefully that's kind of the basics. Hopefully you can sort of conceptualize everything else based on what I told you. It's really just a review. I just wanted to bring up some key topics, not really go through a whole thing because that would take an hour. But yeah, thank you for watching, and hopefully you do well on the test.